In this particular example, we've been asked to determine or at least estimate the volume of this object that sits on a wooden lathe. And it would be nice if we had the equation that represents this curve, because as we've seen with the revolution of solids, if I had essentially this function, the function that describes this shape, and rotate it in this case about say an x-axis, well then we'd be able to use traditional calculus to determine the volume of this object pretty precisely. Unfortunately, however, we do not know the function that establishes this curve, and instead we just have the radius of this object at several different positions. Now, the instructions in this particular example says to use a left-hand Riemann sum estimate to determine the volume of the object. And if I were to take this out of its 3D image here and just kind of redraw this sketch from the XY axis, so I'm going to go ahead and draw one of these real quick. I guess we just need the positive x, don't we? And really the positive y too, because I think we can get by with just plotting the radius. And you'll see why in just a second. So down here, if we're using a left-hand estimate, we're using the first, what's it look like here? 6 data points, and we're going to ignore this 7th because that's on the right-hand side of each interval. But this first section here essentially is going to have a circular slice that has a radius of 6.1. So I'll just draw this here. And I'm going to make a note that the radius in this position is 6.1. Then the next position has a radius of 7, and so on. Now, with each radius established for all 6 of these segments, oops, and I went too far. Should have only done 6 here. For all 6 of the segments, we could essentially find the volume of each one. So the volume of the first segment, I'll call this one the first one here. Well, we have pi times the radius squared. That gives me the area of the circular shape at its end. And then we just have to multiply it by the height or the depth of that cylinder, because these are essentially going to be cylinders. After the radius has been rotated, we have a nice cylinder here. And so now the question becomes, well, how wide, or depending on your perspective, how tall is the radius section, or I'm sorry, the slices section here? Well, we know that the total width of the object is 50 centimeters, and we're separating or segmenting it into 6 widths. So if we took 50 divided by 6, that would represent essentially the height or the width of each section. So I don't necessarily care what the decimal value of that is. I'm just going to take 50 and divide it by 6 and put that into my formula. And taking a look at the instructions, it says not to round until the final answer. So I'm just going to leave this one alone for the time being, and then I would set up an expression to find the volume of the second slice. So here we've got, for V2, the radius is going to be 7, and it needs to be squared, and we'll multiply that by 50 over 6, and so on. And we would repeat that for each of the 6 slices. Now, what I hope you recognize, too, that might make this easier in the long run once you understand the pattern, is that every one of these volumes is going to contain a pi and a 50 over 6. So if I had all 6 of these written out and added them together, we would see that that's a common factor. And so what that might lead me to recognize, even before I finish writing them all out, is that the total volume, based on this approximation method, is going to be 50 over 6 times pi. So I'm going to factor that out, and then of all 6's, or all 6 of these sections, essentially all I need to do is take the radius of each one and square it. So the first radius squared plus the second radius squared plus all the way up to the 6th radius squared. And if we enter this expression into our calculator, especially the TI Inspires, we should be able to obtain a nice result for this particular estimate.